This is the periodic table of the elements, in which elements are arranged according to their atomic number. And these two series, having 14 elements each, are called as F block elements. These two series are called as F block elements. Why these elements are called as F block elements? Because in these elements the last electron enters into the f orbital, that is n minus 2 f energy level or f orbital. That's why these are called as f block elements. These two series are called as f block elements because the last electron enters into the anti-penultimate energy level, that is n minus 2 f orbital. The general electronic configuration of f block elements are n minus 2 f 1 to 14 electrons, n minus 1 d 0 to 2 electrons, and ns 2 electrons, means s orbital is fully filled, but the n minus 2 f orbital and n minus 1 d orbitals are incomplete. Depending upon whether the last electron enters into the 4f orbital or 5f orbital, these are divided into two series. The first series is called lengthenoids. The 4f series is also called as 4f series and lengthenoids, in which the last electron enters into the 4f orbital, and this is also called as first inner transition series. First inner transition series. Why these are called as inner transition elements? This is because the last electron enters into the anti-penultimate energy level, that is n minus 2 f orbital. That's why these are called as inner transition elements. When the electron enters into n minus 1 d orbital, then it is called as transition elements. But in f block elements, the last electron enters into the anti-penultimate energy level, that is n minus 2 f orbital. That's why it is called as inner transition element. And the first series is called as first inner transition series. These are also called as lengthenides, lengthenants, or lengthenoids because they come immediately after lengthenum. That's why these are called as lengthenoid series. Earlier, these 14 elements were called as rare earth elements. Lengthenoid series in earlier days were called as rare earth elements. And the next series or second inner transition series called actinoid series, in which the last electron enters into the 5f orbital, and these are called as actinides or actinons or actinoids because they come immediately after the actinium. Next is electronic configuration of lanthanoids and actinoids. First we will discuss lanthanoids, in which the general electronic configuration of lanthanoids is xenon 54, 4f 1 to 14 electrons, 5d 0 to 1 electron, and 6s2, which is completely filled orbital. And these are 14 elements of lanthanoid series, starting from atomic number 58. Here cerium has atomic number 58 up to lutetium 71. In case of cerium, the electronic configuration is xenon 54, 4f1, 5d1 and 6s2, in which there is 1d electron is present and 1f electron is present. Next is praseodymium, in which the electronic configuration is xenon 54, 4f3. It is 4f3, 6s2. There is no d electron in praseodymium. Next is neodymium, electronic configuration 4f4, 6s2. Promethium, electronic configuration xenon 54, 4f5, 6s2. Then samarium, Sm, xenon 4f6, 6s2. Europium 4f7, 6s2. The gadolinium, this is an exceptional case in lanthanide series. It has electronic configuration of xenon 54, 4f7, 5d1, 6s2. Here in f orbital there are 7 electrons, which is exactly half filled f orbitals, and these are stable. It means gadolinium have exactly half filled configuration, which is a stable configuration. Next is terbium. Here the electronic configuration is 4f9, 6s2, then dysprosium 4f10, 6s2, and continues up to ytterbium, xenon 4f14, 6s2, and the last is lutetium 71, xenon 54, 4f14, 5d1, 6s2. It means lutetium have 14 electrons in the f orbital, means fully filled configuration or stable configuration. General electronic configuration of actinoids is radon 86, 5F1 to 14, 6D0 to 1, and 7S2, which is completely filled. And in actinide series, thorium is the first element and its atomic number is 90. And the last is lawrencium, whose atomic number is 103. The electronic configuration of thorium is radon 86, 6D2, 7S2, then proactinium 5F2, 6D1, 7S2. This is an next is uranium 5F3, 6D1, 7S2, neptunium 5F4, 6D1, 7S2, plutonium. Here it is 5F6, 7S2. There is no d electron in plutonium. Next is americium 5F7, 7S2, curium. This is an exceptional case 5F7, 61, 7S2 due to exactly half-filled configuration. There are 7 electrons in the f orbital, which shows the exactly half-filled configuration. Next is berkelium 5F9 to 7S2, and this continues to nobelium 5F14, 7S2. And the last is lawrencium, in which there are 14 f electrons in 5f orbital and 61 7s2, means fully filled configuration or stable configuration. Oxidation states of lanthanoids. Lanthanoids show mostly +3 oxidation state, means these are more stable in +3 oxidation state, and this is the common oxidation state of lanthanoids, and this is due to the loss of 2 electrons from 6s orbital and 1 electron from 5d or 4f orbital. Oxidation states of lanthanoids. The most common oxidation state of lanthanoid is +3. It means lanthanoids are more stable in +3 oxidation state. And this is acquired by losing 2 electrons from 6s orbital. These are 2 electrons which are present in 6s orbital and 1 electron from 5d or 4f orbitals. They also show +2 and +4 oxidation states. For example, in case of cerium, promethium, terbium, dysprosium, they show +4 oxidation state. In lanthanum, this is promethium and Pr is praseodymium. Holmium, erbium, lutetium, they show +3 oxidation state, which is more stable oxidation state. In samarium, europium, terbium and ytterbium, they show +2 and +3 oxidation state, and in neodymium they show +2, +3 and this is again +3 oxidation state. Here in case of promethium, suppose we take an example of promethium. Its electronic configuration is xenon 54 and 4f5 electrons, 5d0, 6s2. In promethium, it loses 2 electrons from 6s orbital and 1 electron from this 4f orbital and acquires an oxidation state of +3, which is a stable and more common oxidation state of lanthanoids. Next example is of cerium, in which it exhibits two oxidation states by losing 3 and 4 electrons. The electronic configuration of cerium is xenon 54, 4f2, 5d0 and 6s2. By losing its 2 electrons and 1 electron from 4f orbital, it acquires +3 oxidation state. And by losing all the 2 electrons from 4f orbital, it acquires +4 oxidation state, which is more stable for cerium, because after losing the 4 electrons, it left with the stable configuration, noble gas configuration, which is equal to xenon. And next example is of samarium, which shows oxidation state of +2 and +3, and its electronic configuration is samarium. Its electronic configuration is 4f6, xenon 54, 4f6, 5d0, 6s2. By losing 2 electrons from 6s orbital and 1 electron from 4f orbital, it acquires +3 oxidation state. And by losing only s electrons, it acquires +2 oxidation state. Similarly, for neodymium, whose electronic configuration is its electronic configuration is xenon 54, 4f4, 6s2. By losing its 2 electrons from the 6s orbital and 1 from the f orbital, it acquires +3 oxidation state. And only when it lost its 2 electrons from 6s orbital, then it acquires +2 oxidation state. Eurobium 2 positive, ytterbium 2 positive, and cerium 4 positive. Here the electronic configuration of eurobium 2 positive is xenon 54 4f7, and in case of ytterbium it is xenon 54 and 4f14, and in cerium 4 positive it is xenon 54 and 4f0. These are three stable configurations. And similarly, in case of terbium, it acquires 4 positive and its electronic configuration is xenon 54 and 4f7. And in samarium 2 positive, eurobium 2 positive and ytterbium 2 positive. These are good reducing agents. And terbium 4 positive and cerium 4 positive, these are good oxidizing agents. Lengthenoid contraction. It is the steady decrease in atomic size or atomic radii and ionic radii of lanthanoids with increasing atomic number. Lengthenoid contraction is the steady decrease in atomic size of lanthanoids when the atomic number increases. When the atomic number increases, the effective nuclear charge increases, which holds the outermost electrons more tightly, and this results into the decrease in atomic size. And the cause of lanthanoid contraction is the poor shielding effect of 4f electrons, then 3d electrons, which increases the effective nuclear charge, already increased nuclear charge, because 4f electrons have poor shielding effect. They do not shield the outer electrons, and the nuclear attraction reaches the outermost electrons due to the irregular shape of f orbitals. And this imperfect shielding is unable to counterbalance or overcome the effect of increased nuclear charge. It reinforces the increased nuclear charge. Hence, there is net contraction in the size. And when the atomic number increases, f electrons also increases. It means their poor shielding effect increases, which results into the contraction of the attraction on the electrons by the nucleus increases, and hence the atomic size decreases. And this graph shows the atomic ionic radii of lanthanoid series, which decreases gradually or regularly when the atomic number increases. Consequences of lanthanoid contraction. First one is difficulty in separation of lanthanoids. When the ionic radii or the size of the ion is reduced due to lanthanoid contraction, there is very small difference in ionic radii of the lanthanoids. It means their chemical properties are almost similar, which makes the separation of lanthanoids in pure state difficult. This is due to the slight difference in the size of the lanthanoids. And next result or consequence of lanthanoid contraction is similarity in size of elements belonging to same group of second and third transition series. For example, in case of yttrium and lanthanum, they have almost same size, like 180 picometer in yttrium, and in lanthanum it is 187. This is due to the lanthanoid contraction, influence of the lanthanoid contraction. And next is the effect on the basic strength of hydroxides. As the size of the ion decreases from lanthanum 3 positive to lutetium 3 positive, the covalent character of hydroxides increases, means sharing of electrons increases, and hence the basic character decreases. Thus, lanthanum hydroxide is most basic, whereas lutetium hydroxide is least basic, because its tendency to lose electrons decreases. Tendency to share electron increases, means its covalent character increases, and hence basic character decreases. That's why lutetium hydroxide is least basic as compared to lanthanum hydroxide.